Hi, this is clip number 2 in my series on how I created a CNC milling machine from scratch. Check out video number 1 if you didn't see it yet. This is the first electronics video in my series. I will introduce the electronic parts today that I have used and explain how they work together. The usual way of creating a CNC machine with Arduino and GRBL is something like that. We have the 3 stepper motors here for the X, Y and Z axis. They are controlled by stepper motor drivers, for example 3 of the big easy driver boards. The motors are usually 2-phase motors, which means that each motor has 4 cables connected to its own driver board. The big easy drivers are driven by the Arduino, which is running GRBL. The Arduino is connected with 2 cables to each big easy driver when I don't count in the ground line. One cable provides a peak of usually 5 volts whenever the motor is supposed to go one step further. The other cable tells the big easy driver board whether the motor is supposed to go forward or backward. Usually when the line has 0 volts, it means that the motor goes forward, and when the line has 5 volts, the motor goes backwards. The serial port, and in case of the Arduino, the USB port, is used to send G-code commands from the PC to the controller, which are then interpreted by the GRBL and used to drive the machine. When I started planning for this project, I thought I can use this setup and add my LCD and also my keypad. There are several reasons why this plan didn't work. The Arduino has 14 digital IOs and 6 of them are already used for the 3 big easy drivers. This is not all. A CNC machine also needs end switches that tell the controller when one of the borders is reached. They also would need 3 ports at least. Now, my LCD here needs 6 digital lines as well, 4 data lines and 2 for the control, so first problem with that idea, not enough ports. And it does not end here. My LCD is supposed to give a live feedback, so how do I check what my GRBL is doing? GRBL gives the feedback via the serial port of the PC, but it is hard to get this information on the LCD. Another problem also, when I want to use LCD and keypad on that Arduino, I need to add my own software. The problem is that GRBL is basically maxing out the Arduino in memory and also in calculation power. Many functions of GRBL are super time sensitive because it needs to constantly communicate with the PC and give correct pulses to the motors. I really did not want to mess with that awesome piece of software. My solution for the problem? Another Arduino. This one has specific software on it that I wrote myself. It can listen to the keypad and also drive the LCD. It also controls a buzzer, just for completeness. My Arduino is connected to the big easy driver boards as well and can send pulses. So, with that set up, I have what I want. Oh wait, I don't. I still want the live feedback from the other Arduino. I could try to connect the Arduinos via serial port, but this one here already communicates with the computer, so I also cannot mess with that. So what I have done is programming 2 modes into my software. An internal mode where I can control my CNC machine with the keypad, and an external mode where this Arduino here now can read the peaks from the other Arduino and count them, so that this Arduino knows exactly what the motors do and what the position of my machine is. The problem here is I cannot simply connect the Arduinos because, well, let's say both Arduinos are sending data. So let's say this one here sends a low output and this one here on the same port sends a high output. So they can actually damage each other from that, because there is no limit of the current that goes from the one Arduino to the other. I will make another video about the electronics where I explain in detail how I solved that problem and made both Arduinos work with each other. So how do I connect my Arduino? I wanted to drive my LCD. My LCD is a standard 16 characters into rows LCD, which needs 5 volt and it has 6 data lines. The Arduino has 14 digital ports and 6 analog ports. Digital ports 6 to 11 are used for the LCD. There's actually nothing special to say about my LCD. There's even a off-the-shelf library for Arduino to drive it. However, I applied some tricks to make the LCD show what I wanted. I wanted it to show the X, Y, and Z machine position in a 20th of a millimeter precision. You can see the commas which I have put on there with a Sharpie. The two digits before the comma are full millimeters, and the two digits after the comma are basically 1/100th of a millimeter steps, but I only need 1/20th of a millimeter precision, so the last digit is either a 5 or nothing. I also wanted it to show some other info, and so I ended up having only 12 digits for the numbers. The first row displays the absolute machine position, the number of steps for pressing one of the arrow keys, and the distance to travel in one step. The second row displays the X, Y, and Z position for the GRBL Arduino, which is usually starting at 0. Next to that, on the right, the row shows whether one of my border keys is pressed and the moving speed of my machine. Each number has 4-digit space, with no space in between them. The X and Y numbers have to go up to 160, because my bed can move by 16 centimeters in X and Y direction. Theoretically, I would need one more digit before the comma then, so theoretically I don't really have enough space for my numbers. The LCD allows it to define 8 characters pixel by pixel. I used this function to design 7 two-digit numbers from 10 to 16 as only a single character, so that the number before the comma always fits into 2 digits. I have also created a narrow version of the number 5 that I can put at the end of the number so that it is clear to which number the digit belongs. The ports 3 to 5 are used for sending peaks for the X, Y, and Z to the Big Easy drivers, and also to read the peaks on the GRBL Arduino. My port usage setup here will look a little bit weird, and I will explain why. I knew that I need all available ports. When I started assigning ports, I found that the ports 0 and 1 do not work reliably with my LCD. The Arduino ports 0 and 1 are connected to the serial chip, to the FTDI chip, which normally is not a problem, because the serial chip can be switched off. The Arduino that I have used here is actually a cheap Arduino clone, which apparently has another FTDI chip or something, and it seems that it always influences the ports. I ended up using the ports 0 and 1 for less sensitive things. Pin 1 is connected to a piezo buzzer, which makes some noises when I set the port low and high in fast repetition. I'm also using this port to send the direction information to all 3 Big Easy drivers. This works because with my manual control, there's only one movement at a time anyway possible. Port 0 is used for a test where I connect a cable to my drilling tool and let it down on a piece of aluminium foil with another cable attached. I can use this function to determine exactly how long my drill is and also how low I can go without touching any surface. Most digital ports are used by now, but I still need to read the direction information from the other Arduino. The analog pins A5, 4 and 3 are used for that. My keypad is connected to A0. I have used this telephone type 12 button keypad. Normally it would need 12 signal lines to detect each key press. In my setup here I am using only one single analog line, and you can see that the keys are connected to a resistor drain type voltage divider. The resistor drain is connected to ground and to 5 volts, and the signal line is pulled down to ground with a resistor. Now each key press connects the signal line via a different number of resistors to plus, so that each key results in a different voltage at the analog port. I'm using that to detect which key is pressed. The analog port produces values between 0 for 0 volt and 1023 for 5 volts. The Arduino reads the analog port several hundred times each second, and I used the average of 50 reads to detect my key press. At the beginning I had some problems with noise actually, which made my read values vary by ±10 when I pressed the key. For that reason I have added a low pass frequency filter to my connection board, which basically filters away the high frequency noise. With using that filter, my readout numbers vary by less than 1, and I can easily define ranges for each key press. There are still 2 analog ports free, so I use them for the border detection for X and Y. There's actually also some digital ports still free, which I use for the Z border, and another one for a cancel button, which cancels any jogging operation from the keypad. Now, there's an interesting problem with using the ports to read pulses from the other Arduino. The pulses are short, and it is easy to miss one. I could constantly pull the ports in a loop, but then I would not have any time anymore for controlling my LCD or anything else. Some ports of the Arduino have special functions, for example the port number 2 here. It is possible to define a so-called interrupt routine for this port, which is a function that is executed whenever the value of the port changes, regardless of what the Arduino is doing right now. I can use that port to detect any incoming pulse and then count it. The Arduino does not have 3 external interrupts, so I had to apply a trick, which I draw here in a simplified version. 3 diodes are used to connect the 3 peak lines to my interrupt line. The diodes make sure that a pulse from one line does not go into the other, and that all pulses in one of the lines arrive at my port number 2. With that setup, I can still drive my LCD and my keypad, but whenever a pulse arrives somewhere over here, the Arduino executes the count function that then looks up at which port a peak actually arrived. It actually does not work as simple as I have drawn it here. I will explain in another video why. I have made 2 different connection boards for my controller Arduino because I wanted to be able to easily plug and unplug everything. This board here is on the analog side. It connects my keypad to the analog pin here. It also has the pins for the X and Y border detection and for the direction signals for X, Y and Z. Each of the pins gets an own pull-down resistor to ground, which ensures that the port is 0 as long as no signal comes in. It also contains a low-pass filter for my analog keypad. This board here is on the digital side. It has some connectors for the cancel button and for the Z border switch, again including pull-down resistors. It also connects all other digital ports I need. The secret behind this circuit here is something for my next electronics video, and I can generally say that this board went through several revisions before it actually worked. That's enough for today. The next video in my series will explain in detail how I built the machine and all the mechanical stuff from the sliders to the axles. See you next time.